Go. Hello students. Today we'll start with the redox reactions, and redox reaction has been coined from two terms, red and ox. Red stands for reduction and ox stands for oxidation. So those reactions in which both oxidation and reduction takes place simultaneously are called as redox reactions. Simple examples for redox reactions are combustion of fuels. That is a simple example for a redox reaction. Extraction of highly electropositive metals and reactive nonmetals. Manufacture of compounds like caustic soda, caustic potash, dry cell, lead storage batteries, and corrosion of metals involve redox reactions. Also, hydrogen economy and ozone hole involves redox reactions. Let's now define the classical concept for a redox reaction. Firstly, we would see the classical concept for oxidation, and then after we'll see the classical concept for reduction. So addition of oxygen or addition of electronegative element is an oxidation process, and removal of hydrogen or removal of electropositive element is the process of oxidation. Let's see. First, oxidation, addition of oxygen. As you can look in this example, sodium combines with oxygen to form sodium oxide. 4Na plus O2 gives 2Na2O. C plus O2 gives CO2. Addition of oxygen is taking place in both the cases. So it's an example of oxidation process. Similarly, oxidation is a process in which removal of hydrogen takes place. Look at the example. Methane combines with 2 moles of oxygen and it results in the formation of byproducts carbon dioxide and water. CH4 plus 2O2 gives CO2 plus 2H2O. 4NH3 plus 5O2 gives 4NO plus 6H2O. So removal of hydrogen. 2H2S plus O2 gives 2S plus 2H2O is an example of here it comes under removal of your hydrogen taking place. It comes under the process of oxidation. Similarly, it is a process in which addition of electronegative element takes place, oxidation. Magnesium reacts with bromine, giving magnesium bromide. Magnesium is your electropositive element, combines with an electronegative element to form magnesium bromide. Magnesium reacts with nitrogen and it forms magnesium nitrite. Mg3Mg plus N2 gives Mg3N2, is a process of oxidation. Also, oxidation is a process in which removal of electropositive element takes place. Look at this example. Hg2Cl2 gives Hg plus HgCl2. So removal of electropositive element is an example of oxidation. Hope it's clear. Next we come to reduction process. It is a process in which hydrogen is added, electropositive element is added, oxygen is removed, and removal of electronegative element takes place. So addition of hydrogen, addition of electropositive element, removal of oxygen or removal of electronegative element is an example which comes under reduction process. Let's look at the examples here. You can see when hydrogen is added, 3H2 plus N2 gives 2NH3, or CH2 double bond CH2 plus H2. In presence of nickel as catalyst, it results in giving you C2H6. So addition of hydrogen, this reaction is called as hydrogenation reaction. And this takes place in presence of noble metals. Nickel, platinum or palladium as catalyst is a process which comes under reduction, addition of hydrogen. Second is removal of oxygen, HGO, 2HGO gives 2Hg plus O2. So here you see oxygen is removed and it is a process of reduction. Removal of electronegative element. Here you can look at the example. 2FeCl3 plus H2 gives 2FeCl2 plus 2HCl. So removal of chlorine, that is electronegative element from FeCl3, is an example which comes under reduction. 2HgCl2 plus SnCl2 gives Hg2Cl2 plus SnCl4. So addition of electropositive element here, mercury is getting added, and it results in the process of reduction. So this was the classical concept to define the redox reactions. Let's see redox reaction in terms of electron transfer. Oxidation is loss of electrons and reduction is gain of electrons. Remember the code word oil, O-I-L. O stands for oxidation, I is, L stands for loss of electrons. So a process of oxidation, it involves always loss of electrons, and RIG, R-I-G. Reduction is always gain of electrons. So look at the example of oxidation. Iron in +2 state goes to iron in +3 state by loss of 1 electron. This is the process of oxidation that is occurring. Reduction involves gain of electrons. So copper in +2 state gains 2 electrons and it results in giving you Cu. So gain of electrons is a process of reduction. Next, I come to oxidizing agent. Oxidizing agent are species which can gain electrons, and they are also called oxidant. Example, Cu in +2 state, iron in +3 state, Mn in +7 state acts as an oxidizing agent. And those species which can lose electrons, they are reducing agents, and they are also called as reductants. Example, sodium, iron in +2 state, calcium, sulfide S in -2 state comes under reducing agents. And redox reactions are those reactions in which loss and gain of electrons take place simultaneously. They are called as redox reactions. Next, let's come to competitive electron transfer reactions. Here, keep in mind, more reactive metal can lose electron, whereas less reactive metal can gain electrons. Look at this ionic equation. Zn reacts with iron in +2 state to form Zn in +2 state plus Fe. So here, zinc goes to Zn in +2 state by loss of 2 electrons, and iron in +2 state, it gains 2 electrons and it goes to iron, Fe state there, Fe in solid state. Here in this case, zinc is more reactive in comparison to that of iron, and zinc acts as a reducing agent because it can lose electrons, and iron in +2 state is oxidizing agent because it can gain electrons. So this is competitive electron transfer reaction. Here you should know that the more reactive metal, whichever is there, that will displace the other which is present in its ionic state, and it will form the reaction. As in this case, Zn reacts with Fe in +2 state to form Zn in +2 state plus Fe. Let's see the flow chart for this redox reaction. First, let's see the classical idea of redox reactions. Oxidation is addition of oxygen or electronegative element, as I said, and removal of hydrogen or electropositive element. That is the process of oxidation. Reduction is addition of hydrogen or electropositive element and removal of oxygen or electronegative element. And oxidizing agents are those that can add oxygen or electronegative element, or they can remove hydrogen or electropositive element. And reducing agents are those that can add hydrogen or electropositive elements, or they are those that can remove oxygen or electronegative elements. This is the flow chart of classical idea of redox reactions. Let's see the flow chart of redox reaction in terms of electron transfer reactions. As I said, oxidation is loss of electrons and reduction process is gain of electrons. Oxidizing agents are those that can gain electrons and reducing agents are those that can lose electrons. Whereas redox reactions are those in which both loss and gain of electrons take place. Competitive electron transfer reactions says that more reactive metal can lose electrons, less reactive metal will gain electrons. More reactive non-metal will gain electrons easily. And the series of metals in which metals are arranged in decreasing order of their reactivity, that is called as metal activity series. So the metal that is placed above in the reactivity series can displace the metal ion and it can displace the metal which is present below in the reactivity series there. Hope it's clear. Let's now come to the oxidation number. So oxidation number, first you should know the definition of it. It is the charge assigned to an atom of a compound or an ion according to some arbitrary rules. And it is equal to the number of electrons in the valence shell of an atom that are gained or lost completely or to a large extent by that atom while forming a bond in a compound. Let's see redox reaction in terms of oxidation number. Keep in mind, oxidation is a process in which there is increase in oxidation number. So increase in oxidation number of an element in a given substance results in the process of oxidation. Look at the example, iron in +2 state goes to iron in +3 state by loss of 1 electron. So iron in +2 state, from +2 state it is going to +3 state. Increase in oxidation number is a case of oxidation. Similarly, chlorine reacts with 2 moles of FeCl2. Iron is present here in +2 state, goes to 2 moles of FeCl3. So iron here is present in +3 state. So increase in oxidation number is a case of oxidation. Similarly, reduction is a process in which decrease in oxidation number of element in a given substance takes place. Example, 2HgCl2 gives Hg2Cl2 plus Hg. So from mercury here in +2 state goes to +1 state respectively. So decrease in oxidation state is a case of your reduction there. So reduction always involves decrease in oxidation number. And a reagent which can increase the oxidation number of an element in a given substance is called an oxidizing agent, and a reagent which can decrease the oxidation number of an element in a given substance is called as your reducing agent there. So let's look at the oxidation number in terms of oxidation number. We can define oxidation as increase in oxidation number, that is oxidation. Decrease in oxidation number is a case of reduction. An oxidizing agent are those which can increase the oxidation number of other substance, and reducing agents are those which can decrease the oxidation number of other substance. Whereas redox reactions are those that involves both increase and decrease in oxidation numbers. Let's now come to the rules for assigning oxidation number. This should be very clear to you. Oxidation number actually is fictitious in case of covalent species. This number is roughly equal to the number of electrons in valence shell of the atom that are gained or lost completely or to a large extent by an atom while forming a bond in a compound. Let's look at the rules. First rule is the oxidation number of an element in its elementary state always is equal to 0. Example, H2, P4, S8, O2, Fe, Br2 and silver, they have got the oxidation number 0. The oxidation number of an element in monoatomic state or in single ion is the charge on the ion. Example, K plus is having oxidation number of +1. Ca2 plus has got an oxidation number of +2. Al in +3 state has +3 oxidation state. Cl minus has -1 oxidation state. Third rule, hydrogen is assigned an oxidation number of +1 and oxygen is assigned an oxidation number always as -2 in almost all the compounds except in peroxide. The oxidation number of oxygen is -1. In superoxide it is -1/2. Whereas in O2F2 and OF2 it is +1 and +2 respectively. In sodium hydride, calcium hydride, NaH, CH2, KH, NgH2, LiH, oxidation number of hydrogen is -1. Fluorine has also an oxidation number of -1, except in HOF, in which it is +1, but it exists only at -40 degrees Celsius. Usually all halogens have oxidation number -1 except in interhalogen and oxyhalogen compounds. Example, in IF7, I has +7 oxidation number. The oxidation number of alkali metals is +1 always, and alkaline earth metals have +2 oxidation number in all of their compounds. Sixth rule, the algebraic sum of oxidation numbers of all the atoms in a neutral compound is 0. If it is ion, the algebraic sum is equal to the charge on the ion. So following all the rules, you have to calculate the oxidation number of the species that is asked. Look at this noteworthy point. In most of the cases, oxidation number is equal to the oxidation state, but not in all cases. Oxidation state cannot be in fraction or 0. Example, in Pb3O4, average oxidation number of Pb equals +8/3, whereas oxidation state is +2 and +4, as it is a combination of 2 PbO dot PbO2. In CrO5, oxidation number of chromium comes out to be +10, but its oxidation state is +6, as there are 2 peroxide linkages in which 4 oxygen atoms have -1 oxidation state. You can see here, this is the 4 oxygen atoms. They are connected with one another, 2 peroxide linkages having oxidation number of -1. And 1 oxygen atom is held together with chromium with double bond having oxidation state of -2. Thus, overall oxidation state of chromium comes out here to be +6 respectively. Look at the question. Question is, assign oxidation number to the underlying elements in each of the following species. First one is NaH2PO4. You need to calculate for phosphorus here. So phosphorus, the one which you need to calculate, take its value as X. Just now I said alkali metals have got an oxidation number of +1 and hydrogen is assigned an oxidation number of +1, whereas for oxygen atom it is -2 respectively. So here, since 1 atom of sodium is there, +1, plus 2 atoms of hydrogen are there, so +2 +1 +2 plus X, minus 4 atoms of oxygen are there. Since 1 oxygen atom is having an oxidation number of -2, it is -8. So +1 +2 plus X -8 equals to 0. So X equals to +5. So here phosphorus is having oxidation number of +5 respectively. Let's look at the second case, sodium bisulfite. It is NaHSO4 and you need to calculate for sulfur there. So the oxidation number, the species for which oxidation number is to be calculated, we assume that to be X, sodium +1, hydrogen +1, oxygen -2. Oxidation number. So +1 +1 plus x minus 8 equals to 0, x equals to plus 6 respectively. Similarly, for H4P2O7 phosphorus, you need to calculate the oxidation number. So hydrogen plus 1 and oxygen it is minus 2. And phosphorus, we assume that as x. Since 2 atoms of phosphorus are there, it is 2x. So 4 plus 2x minus 14 is equal to 0. 2x equals to 10. X here is equal to 5. So phosphorus is present here in plus 5 oxidation state. Similarly, you take the case of K2MnO4. You need to calculate the oxidation number of manganese here. Potassium is your alkali metal with oxidation number of plus 1. Manganese you need to calculate. So you will assume that to be x, and oxygen it is minus 2 respectively. So 4 atoms of oxygen are there, minus 8. So plus 2 plus x minus 8 equals to 0. X is present here in plus 6 state. Take the case of CaO2. Here you need to calculate for oxygen. Calcium is an alkaline earth metal, so it's having an oxidation number plus 2. So plus 2 plus 2x equals to 0, or 2x equals to minus 2, x is equal to minus 1. So here oxygen is having oxidation number minus 1. Similarly, in case of NaBH4, you need to calculate for boron B. Plus 1 plus x minus 4 will give the value of x equals to plus 3 respectively. Sodium borohydride it is. So hydrogen, since it is linked here with the element sodium, it is having an oxidation number of minus 1. So x is equal to plus 3. Similarly, H2S2O7, sulfur you need to calculate. Plus 2 plus 2x minus 14 equals to 0. 2x equals to 12. X equals to plus 6. Look at the next. KAlSO4 whole twice dot 12H2O. Here you need to calculate for sulfur. Potassium it's plus 1. Aluminium it's plus 3. Plus 1 plus 3 plus. You need to calculate for sulfur it is. SO4 2 it is. So 2x plus 2x. And here oxygen 8 atoms are there, minus 8 plus 24 minus 24 equals to 0, or x equals to plus 6 state. So sulfur here is present in plus 6 state. Let's now look at the Stock notation. So the oxidation number or state of a metal in the compound is expressed by putting a Roman numeral in parenthesis after the symbol of metal in the formula of the compound, and this representation is called the Stock notation, and it was given by German chemist Alfred Stock. Example, Mercury 1 chloride, that is Hg2Cl2, is written in Stock notation as Hg2. I'll put in parenthesis in Roman numeral 1 Cl2. Mercury 2 chloride is written in Stock notation as Hg in parenthesis. I'll be putting in Roman numeral 2 Cl2. So usually we calculate the oxidation number of the metal and we represent that in parenthesis in Roman numerals, and that is how we represent the formula of a compound in Stock notation. So here you look at the question. Question is, using Stock notation, represent the following compounds. HAuCl4. So here you will apply various rules for calculation of oxidation number of the desired element in a compound. And usually the oxidation number of metallic element is calculated. Here the metal which is present here is Au, gold. So plus 1 plus x minus 4 equals to 0. X is equal to 3. So here gold is present in plus 3 state. So it's represented in Stock notation as HAu. In parenthesis, Roman numeral will put 3, 1, 2, 3, Cl4. Similarly, take the case of Tl2O. 2x minus 2 equals to 0, x equals to 1. So we represent as Tl2 in parenthesis 1, Roman numeral O. FeO, iron, X minus 2 equals to 0, X equals to plus 2. So iron, Fe, we'll put in this bracket, parenthesis, Roman numeral 2O. Similarly, Fe2O3, iron is present here in plus 3 state, is written as Fe2 in parenthesis, Roman numeral will put 3O3. CuI, here X, copper will calculate the oxidation number, X minus 1 equals to 0, X is present here in plus 1 state. So we write this in stock notation as Cu in parenthesis, Roman numeral 1I. Similarly, CuO, copper here is present in plus 2 state. So it's represented as Cu parenthesis 2O. MnO, manganese here is present in plus 2 state. So we represent this in stock notation as Mn parenthesis 2O. And MnO2, manganese has plus 4 state. In this case, so it's represented as Mn in parenthesis, we'll write 4O2. So I hope the stock notation is clear to you all. In the next class, we'll be studying about the types of redox reactions. Till then, thank you children and have a nice day.